So Newton's first law says that what objects in motion will remain in motion in a straight line at a constant speed unless acted upon by an outside force, right? So the concept here is the concept of velocity, right? Velocity is a speed, but it's also a direction, okay? And so far all we've done really is dealt with forces that change the speed of an object, but we haven't yet changed the direction of an object. This is what we've done so far, right? So if, say we have an object, hockey puck sliding across the ice, right? Okay, well, if we somehow exert a force this way on it in the direction it's moving, right, then the thing is going to speed up. This would cause a positive acceleration, right? And if I exerted a force this way, like the friction force acting on it, right, that would give it a negative acceleration. In this case, it would slow down because the acceleration is opposite the direction of the velocity. So this, so far, all we've done is linear acceleration. Okay. And we didn't call it linear because we didn't know there was any other kind, right? But that's what it is, right? And we use this formula, a change in velocity. And this was meant to be a change in speed over time, and we figured out accelerations that way. Now what we're going to do is we're going to address the idea of forces that change the direction that something goes. So imagine that same hockey puck sliding across the ice, very frictionless ice. Okay, so here's its velocity this way, right? Now the question is, how do you make this thing go in a circle? Well, the answer is that you exert a force not in the direction it's going, but a force exactly to the side of it. Okay, so if I exert a force to the right as it's speeding along, the thing's going to go in a path like that. Okay, and if I exert a force to the left, well, surprise, surprise, it's going to turn left. Okay, so forces that are at right angles to the velocity are ones that cause it to change direction. Okay. Keep in mind that force, always has to be at right angles to it. So here that force is at right angles. Here it's at right angles. Notice that all these forces tend to point toward the center. Okay, so this force is called a centripetal force. Okay, and centripetal just means toward the center. A centripetal force acts toward the center of a circle like that. Okay. And that's what we're getting into here. That's the new thing, is the idea of changing the direction with a force that's at right angles to the velocity. Okay. So far, all we've done is had forces that were either in the same direction or in exactly the opposite direction. Okay. Now, let's just take a look at this. I'm not going to derive this because doing that requires calculus, and I got to wave my hands a lot, and people don't like it even more. So the formula for this is that the centripetal acceleration is the velocity squared divided by the radius of the curve, right? So if we imagine an object undergoing uniform centripetal acceleration, it'd just be going in a circle. I know my circle's a little bit oval here. That's the aspect ratio got changed, okay? But just imagine that's a perfect circle. This thing is accelerating it's going in a circle like that. It's moving at a constant speed, right? The circle, the radius of curvature doesn't change. The speed doesn't change. Around and around it goes. Okay. Now, I understand that if you're riding in that car, you feel yourself thrown to the outside of this curve, right? So the common misconception is that there's some force acting that way, but it's not a force at all. Remember, if you're in a car and the car accelerates forward, here you are. Imagine you're in, what is that, a Dodge Dart? I don't even know, right? But if that car accelerates this way, if somebody slams on the gas pedal, you feel thrown backwards. You feel thrown back in your seat. You always feel sort of thrown opposite the direction of the acceleration, okay? Just keep that in mind, right? You're not actually thrown backwards. It's just your body is resisting a change in motion. It's the first law of Newton, right? Okay. Now, in this case, you're actually accelerating toward the center. It's a centripetal acceleration. You feel thrown to the outside because that's the opposite direction of the acceleration. You always feel thrown opposite the direction of the acceleration. Okay. And this is it. Also keep in mind that it's velocity squared. So if you double your speed on a corner, you don't double the force needed. You actually quadruple it. If you drive out Highway 26 and you do that little on-ramp to get onto 101 and head toward Cannon Beach, the on-ramp does this crazy thing. It's not shaped like that, like an ordinary one, right? It's like it goes around, big curve, right? Wait. Actually, it curves the other way, right? It curves gradually, and then it's like, nope. There's like this sharp curve, and then you're on 101, right? And you can see all kinds of skid marks. In fact, I think I saw trees knocked down on that curve. Okay. Is there anything else I need to say about that? I don't think so. Okay. In this formula, right, the A is the centripetal acceleration. It actually is in meters per second squared, as we'll see here in a second, just like the regular linear acceleration. V is the tangential velocity. Tangential means that it's tangential to the circle around which you're going. Okay, it's always a right angle, and tangents are right angles to the radius at that point. Okay, and then R is that radius of the circle. And every curve, even if it doesn't go around a complete circle, has a radius of curvature. It's sort of like as if it went around the entire circle, right? And the problem with this radius of curvature on the Highway 26 to 101 exchange, right, is that the radius of curvature changes abruptly. And they try to warn you about that, but we don't believe it, right? Let's take a look at the question here. So we've got centripetal acceleration. We're not going to use the mass here, but we could later, right? Going 24 meters per second around an 80-meter radius corner. So let's figure out the centripetal acceleration. It's going to be v squared divided by r. So that is 24 meters per second. That whole thing squared divided by 80 meters. All right. Let's do this. Okay, so 24 squared that's a big number, 576 divided by 80 is 7.2. It comes out even, right? 7.2. And then the units are, well, the numerator is going to be meters squared per second squared, because we squared meters per second, right? And then divide that by meters. Well, all that does is get rid of one of those meters. So you end up with meters per second squared. Okay, so that's concept zero, right? That's our centripetal acceleration. Now let's just foreshadow a little bit, because I know there's people out there that are like car buffs, right? This is also known as lateral acceleration. Okay, lateral just means to the side. Okay. Like a quadrilateral has 4 sides, right? Okay. A lateral acceleration is they usually do it in G's. So if we have a acceleration in meters per second squared, a G is if you want to figure out G's, it's your acceleration divided by 9.8. Okay. So if I divide this by 9.8, just for fun, you don't have to do this, by the way. This is totally extra. You can just hit stop. I'm going to keep talking here. You get about, this thing is, if I go 7.2 divided by 9.8, I get about 0.73 G's. This is just a pure number, right? It's the fraction of the acceleration of gravity, of lateral acceleration. Now, this is important because if you recall from forces, right, street legal cars can approach about 1 G of any kind of acceleration, okay? Lateral acceleration is difficult for cars, right? Because they're not designed to accelerate to the side. Your typical Econobox can pull 0.8 Gs. That's kind of getting like risky with it, right? A fancy sports car like a Tesla Roadster is approaching 1 G, right? So this is, your parents would be telling you to slow down if you went this fast around that corner. I'm just saying that, right? And then, let's foreshadow some more. By the way, just stop listening to me, okay? If we want to find the force here, all we're going to do is just go m times a. So I'd multiply the 1200 by the 7.2. But I'm not going to do that. That's another video, so